My name's Martin. I work at Chevron with Alex as an HPC software engineer. And today I'm going to be talking about some of the acceleration work on computational stratigraphy using GPUs. So if you went to Tao Sun's talk yesterday, he gave a great overview of how HPC has enabled this new workflow in the oil and gas business. And today I'm going to be talking a little bit more about the HPC implementation and some of this recent acceleration work that's given us some really great results recently. So GPU acceleration. It's no secret that GPUs can make things really fast, really efficient. If you have a highly parallel application, it can really benefit from being ported to run on a GPU. Great speed up, great efficiency, all good stuff. We all want it. This can also lead to simpler infrastructure. If you do have a faster application, you can run it on less nodes, especially nowadays with, you have 8 A100s or H100s packed into a single node. You can really simplify the infrastructure. And this can also be cheaper in a cloud setting, less node hours, less billable time, which is also a good little business value you can throw into a proposal or a success story. But we all kind of get stuck at this last one. They can be very difficult to implement for complicated applications, such as Compstrat, which has a lot of proprietary technology, a lot of complicated coupling, very complicated stencils. This can be a big hurdle. There's a large upfront cost, both in terms of just your development cost, your FTE time, but also in terms of an opportunity cost, right? If your acceleration takes a year or 2 years, during that time, maybe features get added to the original code, and now when you've accelerated it, you might have a really fast new code, but you're a few features behind. Or you kind of need to freeze at a single state, do the acceleration for 2 years, and then resume developing new features. So there's kind of a lot of these hurdles to overcome. So a bit of background on this particular application. Again, if you went to Tao's talk, you saw a lot of pretty pictures like this one. It's a deep water fan being modeled by the Compstrat forward model. And this models the flow of sediment-carrying water throughout the basin as it kind of erodes and deposits material. This is currently computed using finite volume spatial discretization scheme, usually in the form of a Cartesian grid. So a lot of these are square or rectangular domains that we can just split up using a Cartesian grid. So this will be familiar to people who've done finite difference work before. It is compute bound, but luckily it's also parallel. So computing the flow and sediment fluxes for every single cell, updating the sediment deposition. There's a lot of compute involved, but each cell can be done independently of each other as long as you kind of update neighboring information. And currently, the application does use MPI and OpenMP to distribute this workflow, to take advantage of this parallelism. And it still takes a really long time. So most production workflows will take kind of over 2 weeks spread across 32 kind of high-performing nodes, 120 AMD cores. So they are long and expensive simulations to run, which is why they are enabled by HPC and a lot of the HPC work done at Chevron. So what were some of the approaches and opportunities that we saw when we were considering this acceleration? So the first big challenge, as I've mentioned before, is this is a complicated application. This is a research application that's been developed over many years by geoscientists, software developers. There's a lot of moving parts, a lot of proprietary parts, and simply a lot of code. And it has been parallelized, but it's been kind of parallelized as an on-the-go basis in order to transition to larger scale use. You start with a small research test case, slowly you expand to bigger grids, higher resolutions. You need more compute process. You use OpenMP to get more cores. You use MPI to distribute the workflow. But it's still a lot of compute that has to be done. And it's kind of been done in this on-the-go basis as it's transitioned to larger scale use. So the code still has a lot of other opportunities for performance enhancements. No one's ever sat down for an extended period of time and looked at how can we really optimize this code. It's just kind of been developed as R&D goes. But at the same time, it is also used in a few established workflows. So the inputs are kind of meticulously crafted by geoscientists, Tao being one of them. He knows how to put together the boundary conditions, the basin layout, and all of that needs to be fed into a simulation. Similarly, the outputs are visualized and ingested by some post-processing applications. And all of this needs to be able to integrate with this new accelerated version. We don't want to have a brand new version that changes all the inputs, changes all the outputs, and all of a sudden we have to rework a lot of the surrounding workflows. So at the same time, it was not suitable for simply built-in offloading, right? If we want to keep a lot of this input-output the same, maybe we can just offload it using OpenMP offloading or some finite difference library just to change that core section. Well, the finite difference library would be kind of difficult to integrate with our complicated stencil and our sediment coupling that make it just a very complicated application. It would require a lot of reworking of the kind of inner physics and inner mechanisms in order to make that work. Similarly, OpenMP offloading would also be a bit too inefficient because a lot of the parallel sections are disjointed. Maybe a developer writes a Flux kernel and puts that into an OpenMP loop. But that's also joined with a few serial sections in the middle with another OpenMP loop over here. And if you just offloaded those to the GPU, you would have some inefficiencies copying between those two and kind of making that whole orchestration work. Similarly, that doesn't allow us to address a lot of these other performance opportunities that we have. So if we're not actually diving into the code, we can't fix things like inefficient indexing or kind of repetitive calculations that we would be able to by kind of going in and rewriting actual code. But at the same time, we also don't want to do a full rewrite. This is simply a very large task. There's a lot to this application, and there's a lot of code to rewrite. It's also difficult to test and integrate with existing systems. You have to redo your input and outputs. You have to kind of get a lot of knowledge about the overall application so you can start architecturing from the ground up. And this might be the most performant, but from a time to production standpoint, it's simply not feasible. And in fact, it was attempted before I joined the project, and the task was simply too large and too difficult to unit test and compare to the previous application that was deemed not feasible. So at the end of the day, we just need a practical approach that can give us a good speed up, but also fit in with all of these constraints. So the approach we chose was what we kind of call in place. So if you see here, the red and green sections have been changed or added to accommodate GPU acceleration. But critically, our inputs and our initialization, all of our domain decomposition, and all of our outputs remain exactly the same. So this will fit into all existing workflows without having to do any sort of reworking. So if we ignore the red sections for a little bit, this might look very familiar to those that worked with finite difference applications. You have some setup. You then loop through your cells, do all of your flux calculations over and over again, synchronizing that halo every single time. And then every so often you'd get some file outputs. So most of the kind of work, most of the math, most of the science, most of the compute power is spent right here, doing your flow and sediment calculations. That's the most taxing part. That's the part that we really want to speed up. So that's the part that we want to, in this case, we chose to port it to CUDA to take advantage of NVIDIA's GPUs. And kind of all of this surrounding work is to facilitate porting that and getting it to a state where it's GPU native, running at very high speeds. So to start with this one, I would simply search for OpenMP sections within the code. I know that the OpenMP section is already parallelized, so it's easy to port to a CUDA kernel, and I can instantly do a comparison. Right? I have a new CUDA kernel. I have the original CPU code, and I can instantly have them in the same application at the same time, checking each other, and I can instantly compare the speed. So obviously, as soon as you do this with one of them, your overall application slows down. You're doing a lot of copy into the device, a lot of copy out from the device. But you can kind of start to get a sense of how much speed up you're going to expect at the end. So if you compare just the kernel time with the wall time of the CPU chunk of code, you start to see some good speed up. And you can kind of work through this process over and over again until you get all of these sections of code ported to the GPU, and you have a GPU native workflow that just requires data being copied in at the start and data being copied out whenever you want a file output. So that's kind of where we introduce these two sections. So we have hosted device copies and device to host copies. So these bring the data into the GPU right before you get to your main workflow, and these bring it out whenever you want to get it to a file output. So the first challenge that we kind of ran into when doing these hosted device copies is that we wanted to keep this domain decomposition the same. And we also wanted to keep the CPU data structures the same, because that allows us to have a lot more flexibility in swapping these different versions out for one another. So in order to accomplish that, we had to do some index mapping and decompose the CPU data structures into more abstract data structures on the GPU. So at the very start there, you can see in this index mapping, we generate this kind of index map that converts this 2D Cartesian data structures on the CPU code to more linear, directly indexed arrays on the GPU. So with this one, it's easy to write code for 2D. You know exactly where your neighbors are because you know x plus 1, y plus 1, things like that. But you also need to do a lot more index calculations. So you always need to find, let's say you want this xy spot. You now need to compute all of your offsets and get your data directly from some underlying data structure. So this kind of solves that issue. For instance, if you want to iterate over all of the active cells, they have the index that you can directly go and grab your cell data, your velocity, your flow height, and things like that directly from just a directly indexed GPU data structure. This also makes it very easy to iterate through different types of cells. So if you want to work just on the halo, let's say you're doing the NV-link exchange, which I'll get to later, you can just iterate over the halo cells, and you know exactly where to find that data. So that kind of solved this first issue here. So now we have a GPU native code that runs from start to finish on the GPU, copied in data, copied out data. But we had another bottleneck, and that was this halo exchange. So we originally used just the MPI exchange that was built into the original CPU code. So that involved copying out the halo data over the PCI link to the CPU, doing the MPI exchange with packing and unpacking, and then copying it back to the other GPU and putting it into the halo. So of course, the way to fix this, at least on the Azure 8-way nodes that we were using, was to take advantage of the more direct NV-link fabric, which is more direct, a lot faster, way less packing and unpacking necessary. And we did this using the nickel library and we had another index map to grab the correct data from this GPU and place it in the correct spot on this GPU. And that gave us another factor of 2x because it really alleviated that communication bottleneck that came to light once we accelerated the rest of the calculation. Then we ran into one last issue, and that was memory. So as we scaled the applications up and used the great speed up that we were getting from the GPU, we ran into memory issues on two sides. So the first one, and kind of the most obvious one when you're working with GPUs, is device memory. So the device memory was simply not large enough to hold the entire sediment grid. Because the sediment grid also grows as sediment gets deposited. Let's see, this is, for instance, a single cell. Sediment can continue to be deposited up on top of this array, increasing the memory demand of your application. So in order to fix that on the device side, we introduced this fixed size device buffer. And that kind of, in a way, straddles the top of the surface here, because we know that we're only going to use the top few sediment layers in our calculations, and we leave some room for deposition going upwards. So as kind of the simulation runs, let's say this cell deposits 3 layers here. It tops out this device buffer, and then it does the resynchronization only when needed in order to get everything back to the center, which happens anywhere from 10,000 to 1 million iterations, depending on your simulation. But then we ran into the same issue with node memory. So now that we're only using a single node, because we want to really take advantage of the NV-link connection, that memory that was usually spread out over the 32 plus CPU nodes is now condensed into a single node. And even the Azure nodes that have close to 2 terabytes of RAM, this simply wasn't enough for some of our larger simulations. And we quickly ran out of physical memory. So we simply introduced another buffer, this one to go to disk offloading. So this offloaded the data in these lower sediment layers to disk using memory mapped files. This kind of happens whenever we fill up to kind of max out our memory, we can offload a certain amount of the bottom layers, since we know that those are the least likely to be used. They're only going to be used in the case of a very high erosion event, for instance, making a canyon or something. So we know that it's very unlikely they're going to be used. We can offload it to disk, take that hit one time where we have to do the offloading, but then hopefully not have to read it back into memory very frequently and deal with that slowdown. So it's in a way acts as a smart swap. Since we know when memory is going to be used and what's not going to be used, we can get it onto disk and not have to worry about it clogging up our memory. So now we have the full functioning GPU code. We've kind of solved these few challenges. It's time to run some benchmarks. So on the bottom here, we have kind of 5 internal benchmarks, 2 confined channel runs, and 3 deep water fans. These are, for instance, what you saw on that first animation. And on the left-hand side, we have kind of a measure of speed. So this is cells per node second. The cells here kind of normalizes it. So some of these are smaller grid sizes. Some of these are larger grid sizes. So just to get that normalized, we consider cells. And we also normalize it to number of nodes. So you'll notice here we have a classic production run with 32 HBV3s. So that's 120 AMD cores each. We compare it to our most frequent used GPU node, which is an ND96 in Azure, which has 8 A100s. And we see kind of across the board, 100 plus X speed up on those compared to the CPU when it comes to kind of total node hours. For instance, since this is a 32 node run, you can consider that this 100x speed up is, for instance, 3 or 4 times faster, but on 32 fewer nodes. So that's kind of that simpler infrastructure kicking in there. So in conclusion, let me just get a drink of water here real fast. What have we achieved? So we achieved a scalable and efficient GPU implementation for this CompStrats forward model. We reached that 100x milestone that we were hoping for. We've greatly simplified our infrastructure. So now for one of these runs, we only need 1 node as opposed to 32. And we also need less time. It's now a few days as opposed to a few weeks. And this also saves us money in Azure, which is great. And it's also very easy to use and in production. Since the inputs and outputs have been kept the same, we've been able to swap it in for some of our deep water runs. And this is already greatly shortening the workflows for those specific simulations. But there's obviously still work to be done in the future. The first one is to kind of continue that development. Right now that we've done the acceleration, we want to be able to add those new features. So we want to allow geoscientists to add features to the code base, work with the HPC engineers to work on that optimization. So it's kind of a continuous cycle of adding features, accelerating them, and keeping the code base fast. And then there's also the bit about just testing and benchmarking new technologies. As we saw in the benchmarks, our H100s performed about 50% faster than our A100s, which unfortunately is not super economical in Azure, since they're probably going to cost more than 50% as much. So we're going to have to get creative in how we kind of improve performance going forward, how we improve that scalability, potentially use InfiniBand to go multi-node without incurring too much of a communication bottleneck. But this is a continuous work that goes on with a lot of applications. You want to be able to keep it up to date with modern technologies. And some quick lessons learned from this entire process, this whole case study. The first one is to use a more robust unit test framework. So I was able to test directly a lot of kernels directly to the CPU code. But once the problem got big enough, everything was kind of written in GPU kernels. There were some issues that were a lot more difficult to find, because now you have to go back through and dig into which kernel is causing which issue. So if there's a more robust framework, which again is that upfront cost that you have to overcome, it can pay off down the line when it's much easier to find bugs and issues. The second one is to kind of start small and expand your scope. When I first heard of this task, I was like, this is crazy. This is a huge code base. But if you just kind of start on the small sections, you find sections that are already parallelized in this case, for instance, rewrite those, test them right there in the code. You can kind of start this process. And it takes time, but you'll not be overwhelmed by a completely massive task of rewriting a new code base. And the third one is to pay attention to your dependencies. and kind of how to upgrade them, change them. We need a few new libraries for this one. So we needed CUDA, we needed Nickel, and we also wanted to upgrade some of our C++ compilers. So just kind of getting that all in a nice working method is going to be a game changer when you're working through this process and upgrading applications. Now we're kind of doing some work with potentially containers and things like VC packaged in order to make this even easier. So, and that is everything I've got. So I'm going to open it up to questions. We've got 4 minutes.
Yeah, thanks, Martin. And we do have quite a bit of time for questions, so please.
Yeah, hi, Martin. Dean Guma at Eigencontrol. So obviously the name of the game is parallelization and maybe some tricks on memory debottlenecking, but have you thought about, since parallelization is such a big trend, have you thought about parallelization at the stencil or at the discretization level?
Yeah, so one of the first things we considered was parallelization more at the stencil level. But since the stencil is not super obvious in CompStrat, it's a bit more hidden. There's kind of multi-edge bits to it. That kind of seemed like too much of a change for the internal physics engine in order to kind of accomplish that.
Is it still cheaper to run the A100 nodes compared to the 32 CPU? I know it's way faster, less node hours, but is it cheaper as well?
Yes. So since you get roughly 100 times fewer node hours, I mean in some of the cases up to 200 times less node hours, and the GPU nodes cost let's say like 7 times more, you get a pretty substantial cost savings, especially when it comes to applications that run for this long on this many nodes that are already really expensive. That kind of percentage knocks a good chunk off the price.
Last chance? Well, not last chance. Martin is around after this too. Okay, then thanks again.